Greetings and welcome back. So, we just talked about positional information, and that was really the brainchild of Louis Wolpert, for example. And we discussed the paper that he wrote, the idea of the morphogen. We showed how we could write down a sort of generalization of the diffusion equation, which is known as a reaction diffusion equation. And the critical feature of that equation was that we kept track of the same field variables. You'll recall that in our continuum theory protocol, the first element is, decide which kinematic quantities you're going to keep track of. In other words, what are you going to use to describe your system? And so what we did in that case was to use a scalar field. When I say a scalar field, what I mean is that each point in space and time, there's a single number that quantifies the variable of interest. So, I often think of meteorology as a nice way for us to become conversant with things like the scalar or vector fields, because at every point in space there's a temperature. And when you watch the evening news, at every point in space they might show arrows that signify the local wind direction and magnitude. So that's a vector field. The wind velocity is a vector field. So we're keeping track of the concentration field. We wrote down a generalization of the diffusion equation, which accounted not only for the fact that the concentration field of interest can diffuse around. If there are gradients, what will happen is that molecules will move from the high concentration region to the low concentration region. That's all great. But then we supplemented that with an idea of a reaction. And in the case of positional information, for example, in the context of a morphogen gradient, we posited that it was the interplay between production of protein and diffusion of protein and then degradation that led to this steady state exponential profile. The French flag model showed us at least a scheme that positional information can serve as a coordinate system, as an address. I think of it in some ways like Manhattan. On Manhattan you have this north-south series of streets perpendicular to it. You have streets that are numbered, and those numberings tell you where you are on the anterior-posterior axis. If I'll let the anterior part of Manhattan be the southern end of the island down by the Statue of Liberty. So at any rate, we in positional information language, we have this coordinate system. What we're going to talk about now is a very different idea, though it's still based on reaction diffusion equations. And what I mean by that is that we're going to consider more than one species at a time. They're going to all be able to diffuse around, but they also will have the capacity to interact with each other. So this is an idea that probably goes back to many people, just on the grounds that so many things that happen intellectually in the scientific realm are thought of by more than one person. I don't know such a history. I'm just sort of making a general remark. This goes under the name of the Turing instability and refers to the work of the great Alan Turing, shown here. There's quite a story about this poor soul who was persecuted for his personal lifestyle, which was no one else's business. And he was punished in the most cruel of ways, ended up taking his own life. That's for another time, but I encourage you to go look into it. And he wrote a really famous paper, which we're going to talk about, which is called The Chemical Basis of Morphogenesis. I just want to say that he also did important things in the context of computer science, and in fact, there's a really interesting book. If I remember correctly, it's by a guy called Petzold. I think it's Charles Petzold, but I'm not sure of that. And there he basically writes a whole book around another one of Turing's very important papers. And Turing also wrote a really interesting paper on phyllotaxis, which has to do with, when plants are growing, at what angles do you find the new branches pushing out. Anyway, he was an incredibly creative mind, and this is maybe just a little bit of a side note, and perhaps constitutes, once again, overly sharing my subjective opinions, but that's what I'm going to do. And part of the reason that I do it is to challenge people to think about these matters for themselves. And if you disagree with me, that's fine. But also because it's fun to hear people's subjective views. In other words, for me, I recently had a referee tell me, which probably many of you would agree with, that I'm annoying and that our writing style is not appropriate for proper scientific communication. And he was kind enough to identify himself, which I think took a lot of bravery, and we had a nice chat. And I was just telling him, for me, with my attention span and my slowness, that actually I find his kind of writing annoying. In other words, I like it when somebody spells out their subjective opinions and when they use superlatives so that they can give a sense of where their enthusiasms are, and so on. Anyway, okay, so the rant goes like this. We live in this moment of scientific likes. One of the things I find most distasteful about the internet era is that, I certainly didn't see coming, was this weird obsession with likes where, people want to have their content clicked on. There's sort of a scientific equivalent of that as well, which, is trying to judge people by the frequency with which their work is cited. And you might be saying, well, what does this have to do with anything? And I'm just kind of always amused by this idea of the H index, the Hirsch index, which is your Hirsch number is the number of papers that you have that have been referenced at least that many times. So for example, if your H index is 50, that means you have 50 papers which have been cited at least 50 times. And the reason I bring this up in the context of Turing is that I always think about some of my personal heroes. So in my office I have a picture of Josiah Willard Gibbs, and I think his H index must be something like 23, because I don't think he wrote more than about 23 papers. And Feynman's total output in terms of body count, in terms of how many papers he wrote, is also nothing like some of the cases that you see these days in people's publication lists or CVs or whatever. Probably somebody that none of you have heard of that was one of my really great heroes in my former life in condensed matter physics is a guy named Jock Eshelby, who was a mechanician and did a really cool thing that's actually related to something we're going to talk about later, which had to do with generalized forces and how we find the forces on defects like dislocations and cracks. And he had a series of wonderful, very deep papers, but he also, in his career wrote less than 100 papers. And, on the subject of Turing, there's, it's a similar thing. There's not 1,000 papers that he wrote in his career, and yet, I think I'm just trying to say that I dare say that I don't know anybody that's living with an H index of more than 100 that could be compared to Gibbs. Maybe I'm wrong. I don't know. It doesn't really matter that much. It's mainly just to say that that this idea of number of citations of numbers of papers is fine, and that's interesting. I think it is interesting to see, but people like Turing belie that kind of worldview of trying to assess people's merit. Okay, so that was a long digression, and let me circle back to the main point here, which is there are all sorts of interesting patterns in the biological world, and one of those patterns is the long axis of the fly with its segmented body structure. That's awesome, and we talked the other day about the positional information and morphogen gradients as possibly being the origin of that. But once upon a time, one of the ideas was that maybe the stripes in the gene expression pattern of the early fly embryo were the result of a spontaneous symmetry breaking of the kind that we're going to discuss in the next vignette mathematically using the ideas of Turing, which will, in a very nice way, bring us back to the linear stability analysis that we did in the mutual repression switch. That's one of the reasons I did the linear stability analysis. I wanted to give you a first acquaintance with that idea so that you'd be ready for it when we did it this second and third times, which will be in the context of Turing. So, there's all sorts of beautiful examples at the top. I think I'm showing you an example of the Belousov-Zhabotinsky reaction. I hope I said those names correctly. Sometimes I forget. There's these beautiful patterns on seashells and then fishes, and I recommend to you the work of Kondo, who has been taking the Turing idea seriously. So let me just give a little bit more editorializing here. So it became, in some sense, popular to dismiss Turing as wrong, and part of the reason is because of exactly this question of the stripes and the fly. And that wrongness is super interesting, and super Baroque in a way, because, each stripe is its own story. It has its own enhancer, it becomes its own story. But the fact that that's not a Turing instability hardly demonstrates that, therefore, the Turing model is invalid or uninteresting for biology writ large. And, what I'd say is over the last 10 years that people have resumed investigating the Turing model in a very careful way. And this harkens back to something I said in an earlier vignette about the MWC model of allostery, the Monod-Wieman-Schage model. So over the last 10 years, I wrote a book called The Molecular Switch. Not that I'm bragging about that. I'm just telling you, I spent a lot of time thinking about allostery. And that included interviewing many, many people and also just listening to people. And what blew my mind in the end was not only the harsh feelings that remain over the distinction between the MWC and the KNF model. I already mentioned that in a previous vignette, how to me they're just kind of different trivial examples of the same stat mech. I don't really think of them as being particularly different, but people are passionate about them as being different ideas. But the other thing I wanted to say is the very strong opinions that are held about whether or not MWC is wrong or too simple or whatever, versus it's obviously right, and therefore there's no reason to test it further. And what I can tell you is that both of those views have been expressed to me very strongly, but they're mutually exclusive. They cannot both be true. So, if people are passionately certain of those two views, it starts to worry you about, what consensus means and the role of gossip in our science. And so, as I mentioned, I feel like, the definitive treatment of hemoglobin using the MWC model is only within the last 5 or so years by the Israeli group. And it's beautiful work, published in PLOS One because it wasn't deemed of sufficient general interest or whatever. As usual, I'm going to be a bit of a contrarian, and I just very much disagree with that. I think it's the careful study that shows us the extent to which one can trust the MWC model in that setting. And, we also did a similar thing, which I talked a little bit about with respect to transcription factors and induction as an MWC phenomenon. Now, what does that have to do with this? It's just to say that in the hands of people like Kondo, in the hands of people like Sharp, who's at ENBL in Barcelona, Michael Stumpf, and others, people are revisiting the Turing ideas with a bit of a more open mind, with a little bit of a more generous idea about what it means to be wrong. You'll remember that I gave you this story in a vignette about surprise, about the long history of the specific heat of crystalline solids. And, we still teach the wrong model of statistical mechanics of specific heats in classical physics because it's eminently useful and eminently interesting. And the failure of the model is interesting and points a tangent vector in the direction of quantum mechanics. So this notion of wrongness, I think, is very slippery, and we need to take more caution. So all of that is simply to say that I think that the jury is still out on the extent to which there will be broad reach to this idea of the Turing instability. And, one of the examples that maybe I'll have a chance to talk about is the digits, for example, in our hands, and what counts them and whether or not they might be a Turing type instability. I will try to get to that in the next few vignettes. Okay, so with all that as a very long-winded background, this paper from Turing the chemical basis of morphogenesis um, makes this model, and there's famous quote in here which I feel like I should read. One part of the thing. Well, with either of the models, one proceed. I don't know. Let's see. I'll just read the abstract. It is suggested that a system of chemical substances called morphogens reacting together and diffusing through a tissue is adequate to account for the main phenomena of morphogenesis. Such a system, although it may originally be quite homogeneous, may later develop a pattern or structure due to an instability of the homogeneous equilibrium, which is triggered off by random disturbances. And if you fly around in an airplane, I often see it over the middle of the country. You might be flying over Kansas. You see these beautiful lines of clouds, and these are convective rolls, which are also an example of an instability. Such reaction diffusion systems are considered in some detail in the case of an isolated ring of cells, a mathematically convenient, though biologically unusual system. The investigation is chiefly concerned with the onset of instability. It is found that there are 6 essentially different forms which this may take. So he goes on to say something about that. The purpose of this paper is to discuss a possible mechanism by which the genes of a zygote may determine the anatomical structure of the resulting organism. The theory does not make any new hypotheses. It merely suggests that certain well-known physical laws are sufficient to account for many of the facts. So he says this model will be a simplification and an idealization, and consequently a falsification. It is to be hoped that the features retained for discussion are those of greatest importance in the present state of knowledge. So let me just foreshadow then what's going to happen. We're going to start out with what we will refer to as a 2-cell model. So what we'll think about is 2 species. Let's call one of them an activator and one of them an inhibitor. We have 2 cells, which I show here as hexagons, and those 2 cells have the capacity to react, in the sense that the activator can activate the production of activator and of inhibitor, and the inhibitor can tune down the production of activator. So that's the chemistry part of this. And then there's also the diffusion part. And what is strange and interesting here is that we usually think about diffusion as smoothing things out, but what we will find is that there are circumstances under which, if the diffusion coefficients of those 2 species are sufficiently different, there will be an instability. And when I say instability, what I mean is that the system a perturbation, a finite wavelength perturbation, will grow over time. In other words, if you start out with a homogeneous state, it will be unstable to the emergence of periodic patterns. And so that's the thing that we will try to do. We'll do it first for this 2-cell system, because that will teach us how to do all the relevant math and also the linear stability analysis. And then what we'll do is we'll turn to exactly what he just said, which is the ring of cells. All he really meant by that was periodic boundary conditions. And then we will ask the question, is this ring of cells, or is a one-dimensional array of cells unstable to the emergence of a pattern, a periodic pattern, and the pattern will be characterized by the concentrations of X and Y, the 2 morphogens, as a function of their position. So that's the idea. So we will have a physical concept, and we will also have a mathematical implementation of that concept. Together, those 2 things will give rise to our insights into the so-called Turing instabilities. So that's what I have by way of background for this topic.